All right, guys, math one, math one, oh wow. Math, guys, math 1500 here, central limit theorem. You'll probably notice that my voice is struggling. Sorry. I guess I'm having summer allergies or something. I have no idea. But anyway, it's kind of annoying. And I even consider not putting up the video because I know it's going to be annoying. But I decided to anyway because I don't want to get behind. What I'm going to do here is I'm going to get into chapter 7, specifically section 7.1, 7.2, and 7.3. 7.1 and 7.2 will be what we'll cover in this video. I'll put another video up later covering 7.3, and then I'll put up another video next week that will start going over this in more detail. So we'll start throwing all the problems in together and see if we can differentiate between the types of problem we have. Let's just go ahead and get to what we need to get to here. In statistics, the word distribution, or more specifically for us, distribution shape, tends to play an important role. And in conjunction with the distribution shape, we like to be able to define appropriate center and spread statements. Now, this is exactly what we did with the normal distribution. The shape was perfectly bell-shaped and symmetric. Again, realizing, keep this straight here, thinking when you see that this thing came from a histogram that was perfectly bell-shaped and symmetric, that was smoothed out this way. So in what we just covered, the distribution shape was a normal distribution. Its center was defined by the mean, which we knew the location was smack dab in the center of the distribution. And the spread was defined by the standard deviation, which is that distance between, we talked about in the previous video, this linear part of the, if you draw a normal distribution correctly. So this would be mean plus one standard deviation, or a standard deviation above the mean. So the things that we just started or finished covering, the normal distributions, again, the shape is normal, the center is mu, and the spread or consistency is the standard deviation. If we know these measurements, then we can completely define where a normal distribution is going to be. So guys, if we have a normal distribution with a mean of say 20 and a standard deviation equal to 5, then that tells us that on the axis that our distribution, it'd probably help if you guys could see that, right? Our distribution is centered at 20 and 5 units to the left and 5 units to the right. We have this place where our distribution kind of forms a straight line. Those things are kind of hard to draw, but anyway, guys, we know the shape, we know where our distribution is centered, and we know where what the spread around the mean looks like. Guys, we're going to build upon that now, and we're going to get into something called sampling distributions. And sampling distributions play an important role in heading into big boy, big girl statistics, which we will start into after your midterm. So sampling distributions just ultimately tell us how would all samples behave of size n from a large population. Now guys, let's think this through. All right, from here on out, we're going to spend a lot of time looking at the relationship between samples and populations. And the reason being is samples and populations and the dynamics between the two serve as a basis for us to make to perform inference, which is the, in my opinion, the most important thing that we do in this class. Now, looking at the relationship between a sample and a population, let's say, for example, that Tim Hortons, so let's go down here at a goal. Tim Hortons, just in Portsmouth, would like to know the mean wait time for drive-through customers. Now, does anybody know that? Well, you might say, well, yeah, I saw that it was published somewhere. Even if it's published, you don't know it, okay? But let's say that we'd like to know that and we want to carry out a study. Now, the population here would be all wait times. Guys, I mean literally all. Forever. Well, for obvious reasons, we can't collect all wait times forever. So what we would want to do is we would want to collect a sample. So what we could use here is we could use information from a sample to make a statement about a population using what's called inference. And guys, this is the end goal. The end goal here in this class is inference. And again, we'll start that right after we take our first, take our midterm. Now, in this situation, our sample is known because we can go take a sample. Let's say we just decide to take the next 50 customers at Tim Hortons, and we take the measurements. Okay, so the first one took 3.8 minutes. The next one was 2.7 minutes, and so on and so forth. And then we had, let's say we had a really long wait of 11 minutes. So we have 50 measures here. That we could collect. Now, we would know our sample. All we'd have to do is add up these numbers and we would get our sample mean of these 50 measurements. And we could use that to estimate something that's unknown in our population. Now, before we get into that, we're going to look at the other direction called probability. Because everything we're going to use, everything I'm going to teach you down here is going to be ultimately the cornerstone for what I teach you up here. In this situation, probability, what's known and unknown reverses. In probability, the population is known, but the sample you draw from it is unknown. So let me explain what I've got here. Let me explain what I mean by that. So let's say that I come into a class sometime and I pull 5 cards. Out of a standard deck of cards of 52. And let's say I have an ace, a king, a queen, a jack, and a 10. So what is the probability that at random I choose an ace? Well, there's one way to choose an ace out of 5 total ways. So the probability would be 0.20. My population in this case would be these 5 cards. The sample would be what I would choose. Now guys, if this is truly at random, if these cards are face down, then the likelihood of me getting an ace is random. I don't know what I'm going to get. Therefore, my sample is unknown, but my population is known. Now, what if I come in with 5 other cards a couple minutes later, but I don't tell you what they are, and I ask you what's the probability of getting an ace? Well, you can't tell me because you don't know your population. I may have played something silly here and brought in 4 10s and a 9, in which case the probability of getting an ace is 0. So guys, long story short, when you're determining the probability of getting something from a population, you have to know all of the important conditions and characteristics of the population that you're actually drawing from. But if we have true randomness, our sample that we draw is unknown. We don't know what we're going to get from our population because, again, with true randomness, the sample that we draw is unknown. So, guys, going back to the original drawing, before we get into inference, we're going to get into this thing called sampling distributions. And sampling distributions ultimately relies on this relationship right here, that when we know the population we're drawing from, we can determine the probability of getting a particular sample from it using, again, the laws of probability, or at least the properties of probability. Now, let's go on and get into sampling distributions, and let's talk about what these things are all about. Sampling distributions describe how samples will behave. And I don't mean behave in terms of like trying to get a 4-year-old kid to behave. I mean, what's the behavior? What are they going to look at? What are they going to look like? And from previous discussion in this video, what would we be interested in? The shape of the distribution, the center of the distribution, and the spread of the distribution. If we can accomplish, and we will after this video, what happens with our sampling distributions in terms of describing the shape, center, and spread, then we are going to make tremendous jumps forward in terms of understanding more about inference once we get there. All right, gang, here's what happens. Imagine starting out with a population. I'll tell you what I want. Yeah, let's just do this. Let's say we start out with a population where the mean and the standard deviation are known. Now, why do we have to do that? Well, because of this right here. The population that we draw from has to be known because we're going to explore the probability of getting particular samples from it. So the population that we draw from has a mean and a standard deviation that is known. The way the central limit theorem works, we start focusing on a sample size. And it turns out when n is greater than or equal to 2, we have to be assured that we have a normal distribution that we started with back here. If n is greater than or equal to 30, then any distribution will work for what I'm going to try to teach you. So if you think about it, this population that we start out with is either going to be a normal distribution or it's going to be something else. I just call it a not normal distribution, or it's unknown. Positively skewed distribution, negatively skewed distribution. It's any, I should say, other distribution other than a normal distribution. If we're assured that we have a normal distribution, then all this stuff that I'm getting ready to teach you, sample size greater than or equal to 2, is sufficient. If we have a positively skewed distribution or a negatively skewed distribution or an unknown distribution, then we need a sample size of 30 or bigger for all this stuff to actually take place. Now the next step in this crazy game is to begin taking random samples. But you only do this after you set your sample size. So let's imagine that, contrast this with what we've done in previous problems. Previous problems with normal distributions, we take scores out one at a time. We examine scores one at a time. In other words, we could say that IQs form a normal distribution with a mean of 100, standard deviation 15. A person is selected at random. What is the probability? Their IQ is above 122. Well, guys, we should know how to do this with no question whatsoever. Since we're asked to find something that starts with a P, we're going to use normal CDF. We went above 122. Mean of 100, standard deviation 15. So in our calculator, that's the way we would work that problem. So let's just go ahead and work that, just so everybody's cool with this stuff, right? So distribution, normal CDF. So we got 122, comma, E99, comma 100. And really the main reason I'm doing this is for those of you that have the old operating system on your calculators, which is fine. It just, the keystrokes enter just a little differently. So enter, so we're going to get 0.0712. I like to think about this in percentages. So that's about 7%. So only about 7% of people has IQ 122 or higher. So the probability would be 0.0712. Now, guys, if the motivation here is to conduct inference. Well, let's see where we currently stand in this statistics course. All right? What do we currently know how to do? We know, let me just start over here. So far, then we have a sample, and we have a population. We can determine the likelihood using probability of getting a sample of size n equal 1, right? A person, right up there, a person's n equal 1, one person. That we know from a population, and the example I used here were IQs, mean equal 100, standard deviation equal 15. That we can determine the probability of getting one person with a particular IQ, well, actually a particular region of an IQ, so we're saying above 122. We could do less than 115. We could do just any calculation that we want. But guys, if this vicious cycle does work, and trust me, it does, if this vicious cycle really does work, where what we learned down here is applied up here in terms of conducting a study, would you feel comfortable conducting a study based on one person? That'd be pretty silly, wouldn't it? You might think, well, what is, the average blood pressure, the systolic blood pressure, and you go out and you get one person, and they just happen to have, an excellent blood pressure of 118/78. Well, that doesn't mean everybody's got a blood pressure of 118/78. That's just one person. So ultimately, when we want to conduct inference, we would want to have a study based on more than one person. So therefore, guys, when we start out with this population, we need to explore probability of samples that are bigger than 1. Well, guys, that's exactly what we're getting ready to do with this central limit theorem thing. So let's go back and start this over a little bit. I know I'm being repetitive, but I think repetition is good in a situation like this. We start with a population. Where the mean and the standard deviation are known. This population that we start with is either a normal distribution or not a normal distribution. If we have a normal distribution, we have the luxury of being able to work any problem as long as the sample size is 2 or bigger. If we have something that's not a normal distribution, then we have to bump up our sample size. For all this stuff that's getting ready to happen down here, we need to bump up our sample size to 30 or bigger. Now, next thing, as I told you before, start random samples. So we go into this population, and the very first thing that we do is we set n. And just for me speaking this through, let's say that n is equal to 80. So what I'm going to do is I'm going to go into my population and I'm going to pull out 80 numbers, 80 measurements, 80 subjects from the population. I'm going to add up all the 80 scores and I'm going to get my first sample mean of size 80. I'm going to throw these 80 people back into the mix. Imagine going in and mixing them up with your hands, if you will. I'm going to pull another 80 people out. I'm going to get my second sample mean of size 80. Guys, I'm going to do that again. I'm going to do that again. And ultimately what I'll think about is I'm going to think about doing that forever. So imagine you start out with the population, you set your sample size, you go into your population and pull out in this case 80 measurements. You add them all up, divide by 80, and you get your first sample mean. That's what that 1 stands for there, just the first one. You go in, get 80 more observations, measurements from your population, selected randomly. You add them all up, divide by 80, you get your second sample mean of size 80. Do that again and again and again. Guys, this is called the distribution of sample means X bar. So how many do we have? Well, we got a bunch of them. We got infinitely many of them. But what happens when we do a study is we have one of these. And we use one of these to actually make important decisions about whatever whatever we're conducting our study on. Now, what would I like to know about this distribution of sample means? 3 things. I'd like to know the shape. I'd like to know the center. And I'd like to know the spread. So I've got these infinitely many numbers right here. Imagine, let's say this first one is 110.2, and this is 111.7. This is 113.4. I don't know what they are. Doesn't matter. We're not worried about that now. We're just creating something theoretically. But imagine we could put all these infinitely many numbers in our graphing calculator, say in L1. I'll tell you right now, our graphing calculator wouldn't handle that many numbers. But let's say we could. And let's say we could hit the histogram button. We could hit one variable statistics and find the mean, and we could find the standard deviation. What would we get? Well, it turns out that the shape, and I will tell you this comes from the central limit theorem. The central limit theorem tells us that the shape is a normal distribution. Well, that's cool. We know a lot about those things because we just studied them. They look like this, don't they? And we know that these two things are defined by their center and their spread. Well, guys, new notation here. Their center of these sampling means. So let's talk about this. We got two conflicting notations here. The mu stands for the population mean. Well, that's what we want, right? We created a new population of these means, so we want to find the mean of those sample means. So to let that notation be more appropriate or be appropriate, we would say that we want the population mean of the sample means. Well, guys, it turns out that it's exactly what we started with back when we defined our population that we were dealing with. It's that value right there that's known. The spread, it turns out to be, is denoted as sigma sub x bar, because we not only want the standard deviation, we want the standard deviation of the sampling distribution of the sample means. Guys, this is found by taking sigma divided by the square root of n. Now, this thing is often referred to as the standard error. So, guys, we know smack dab in the center of all these x bars that we could create from our initial population, they will be centered at mu sub x bar, and that difference between the mean and that magical point right there that we've talked about is called the standard error. So guys, by now you might be scratching your head thinking you wish you'd chosen a different major where you didn't have to take a statistics course, because we got a lot of notation, don't we? First of all, let's just talk about mean. What all have I thrown at you? I've thrown those three at you, right? I've thrown x bar, I've thrown mu, and I've thrown mu sub x bar. Guys, this is the sample mean. This is the population mean. And this is the mean of the distribution of sample means. Taken or created by n measures. These up here are created one at a time. We've talked about standard deviation. Sx, sigma, sigma x bar. What's the difference? This is the sample standard deviation. This is the population standard deviation. And this is the standard deviation of the distribution of sample means taken by n measurements. Now guys, after all the smoke clears, what does that tell us? Well, it tells me this. I start with a population that is normally distributed. It has a mean of 40 and a standard deviation of 5. I collect all sample means all possible sample means from this population of size 10. So I go into this original distribution. That has a mean of 40 and a standard deviation 5, and I pull out 10 measurements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I add them all up. I divide by 10, I get the first sample mean. I do that again. I do it again. I do it, in theory, forever. What have I got? Well, I've got a bunch of sample means that I call the distribution of sample means. The central limit theorem tells me what about these values? They will be normally distributed. They will have a mean equal to the original population mean, which is 40. They will have a standard deviation equal to the original standard deviation divided by the square root of n. Original standard deviation is 5 over the square root of n, and we took these things out at what, 10 at a time? So guys, let me grab my calculator. So 5 divided by the square root of 10 is 1.5811. So my distribution of sample means is going to be centered the same place as this distribution up here. But notice that the standard deviation up here was 5, and the standard deviation, we call it the standard error if we want to get fancy, but nevertheless it's still just a standard deviation. It's a measurement of consistency, measurement of variance, measurement of spread, has decreased down to 1.58. The reason being is when we collect measurements from this distribution, we've got a very much a likelihood of getting something around the mean. So we're going to restrict the variance on our sampling distribution because most of our measurements are centrally located around the mean. So one standard deviation above the mean here is going to be 41.5811. Where one standard deviation above the mean when we're taking things one at a time is 45. We create less variation around the mean when we take things 10 at a time. Now, guys, this opens up a plethora of different types of problems. Now, one more thing before I go any further, I don't want to get ahead of myself here. To revisit something that we talked about previously called z-scores. If z-scores weren't hard enough, we now have to think about z-scores twofold. We have to think about z-scores when we take things one at a time, and we have to think about z-scores when we take things 2 or more at a time. When we take things one at a time, we focus on a particular raw score, x. When we take things 2 or more at a time, we focus on the measurement that is the collective the measurement, if you will, of the 5 scores. So if I collect 5 scores, I'm just going to add them up, divide by 5, and I'm going to get the sample mean for those 5 scores. Well, guys, the z-score, as we've looked at before, for this situation is x minus mu divided by the standard deviation. Now, what do you think the z-score is going to look down here? Same thing, z, right? But what takes the place of x? Down here, x bar. What place takes the place of mu? Mu sub x bar. What takes the place of sigma? Sigma sub x bar. Guys, central limit theorem tells us that mu sub x bar is exactly mu, and sigma sub x bar is sigma divided by the square root of n. I'm going to put parentheses around that because that sometimes turns out to be an issue with students. All right, guys, let's start working some stuff. All right. Now I'm going to get my, let me see if I can find my, yeah, I'm going to use this quite a bit. Okay, so let's make sure that we can even do the problems that that we can, that we have in front of us. Okay. So the first problem, so the engineers must consider the breadths of male heads when designing motorcycle helmets for males. Men have head breadths that are normally distributed with a mean of 6 inches. And well, that's interesting. Okay. And a standard deviation of 1 inch. These results are based on anthropometric, well, that's pretty fancy, survey data from Gordon and Churchill. So guys, if one male is selected at random, what's the probability that his head breadth is less than 6.2 inches? Now, guys, that problem doesn't apply here because these problems right here deal with means. And a lot of times students will say, well, I can't do this problem. Well, you could do it before we started. And guys, there's no reason you can't do this now. If one male is selected at random, what's the probability his head breadth is less than 6.2 inches? Guys, just like we did before, one at a time. Second function distribution, normal CDF. Less than 6.2 means we start with E99. Negative E99, I'm sorry. We go up to 6.2. We have a mean of 6 and a standard deviation of 1. So guys, 0.5793 is the answer to that problem. Now the next thing says the Safeguard Helmet Company plans an initial production run of 100 helmets. Find the probability that 100 randomly selected men have a mean, key word there, head breadth of less than 6.2 inches. Now guys, that's where we get back into these problems. This is where we get into a normal distribution, not normal, sample size restriction, and then we start our focus on how would the sample means behave. Well, that key word right there tells you that this problem falls in the central limit theorem type of problem. So what I would need to do here is I'd want to work the problem the same way. Less than 6.2. Is negative E99 up to 6.2. Standard deviation, I'm sorry, the mean is 6. Guys, in these problems, what do you have to do? You have to divide the standard deviation by the square root of the sample size. Well, guys, we have a sample size here of what? 100. So the correct answer would be 0.9772. Guys, notice the difference in the answers there, where both problems look at a head breadth less than 6.2. But this one focuses on one person, and this one focuses on an average of 100 people, well, 100 men. And it's kind of like this. Think about I know none of you have a strong background in probability, but think about it this way. You're walking down the street and you randomly select one person. What's the probability they have an IQ of 120 or higher? Not very high, but it's possible. Walk down the street and choose 100 people. What's the likelihood that their average IQ is greater than 120? It's not going to happen. You're going to get, when you pull from the distribution of IQs centered at 100, you're going to get some above, some below. It's not reasonable to think that in the distribution of IQs, which has a mean of 100, standard deviation of 15, and you're up here at 20, that you're just going to get values around here where it averages out about 120. It's not going to happen. You're going to get some below, some above, here, there. They're just going to, these means that you collect are going to kind of balance out across the mean. If you get something centered about here about 120, which is very few observations there to begin with, then you probably got a sample collection issue. But taken at random, 100 people has an average of 120 or higher. Not going to happen. No way. In fact, we can actually figure it out. I'll tell you right now, it's very low. So normal CDF, an average IQ of 120 or higher, mean of 100, standard deviation of 15, but we're taking those. I said get 100 people. Yeah, you might say, well, it's 7 point. Guys, probability has to be between 0 and 1. That's telling you that you got to move the decimal place 41 places to the left. So I need to pull that over one place and keep moving it 41 times to fill in with 40 zeros. So in essence, the probability is 0.0000, pretend I said 40 zeros, 77. That's not going to happen. It's just not going to happen. It is extremely rare. You have a lot better probability of winning the lottery, and I mean a lot higher probability of winning the lottery than randomly selecting 100 people with an average IQ of 120 or higher. All right, let's go on to number 2. Women's heights are normally distributed with a mean of 63.6 inches and a standard deviation of 2.5 inches. Guys, this is what? That's our population. And since it says we have a normal distribution, we have no sample size requirement. We can work all problems that start with a normal distribution. So if one woman is randomly selected, what is the probability that her height is greater than 62? Let's do it. (62) up to E99. Mean of 63.6. Standard deviation 2.5. All right, everything look good? Yes. 0.7389. Now, if n equals 36, okay, now sample size is bigger than 1, isn't it? What should I think? Central limit theorem. Guys, when we have sample sizes bigger than 1, we kick in the central limit theorem, the sampling distribution stuff that I've been teaching you now for the last hour. So what is the difference in working this problem and this problem? Well, it's a different type of problem, but at the end of the day, what's the difference? Not much. I just have to divide the standard deviation by the square root of n instead of using the standard deviation of 2.5. So guys, I got the same problem I had before, and I could go second function entry to make a point. I don't need to change anything except divide by the square root of the sample size. That's the only way in working these problems in the calculation of the correct answer. That's the only thing that changes. And I can scream, yell, jump up and down, and I've done it in class before, just got crazy, to make people understand that there's no difference in those types of problems and problems that we were actually pretty good at with normal distributions. So guys, 0.9999, well, that's interesting. So 0.9999, you can almost rest assured that if you go out and select 36 women at random, that their average height, 62 inches, is what, 5 foot 2 inches? You can almost be guaranteed that the average height of 36 women selected at random is going to be bigger than 5 foot 2 inches. All right, next thing, find and interpret the z-score for a sample of n equal 50 women. Well, guys, that tells me that I've got the new type of stuff that I'm working. So I have to look at the new type of z-score for this new type of problem. So guys, remember that the new type of z-score took the mean, sample mean, minus the population mean, divided by sigma with the square root of n. Now, I don't know if you guys can see this or not. Maybe I need to work it this way actually. Yeah, you guys should be able to see that. All right, so find and interpret the z-score for a sample of 50 whose average height is 64.2. Mean comes from a population, that's 63.6. The standard deviation comes from our population, which is 2.5. So guys, putting this in a form that is not quite so messy. 64.2 minus 63.6 divided by 2.5 divided by the square root of 50. Now guys, it's really important that you use parentheses here to keep from getting order of operations problem. So I'll show you how to do it on your calculator. Guys, numerator needs to be in parentheses, so we'll do that. And then divide, and guys, put your denominator in parentheses too. Okay, then you'll get the right answer of 1.70. Now, I see students all the time that evidently they get careless or whatever, or they think they know more than me. And you probably do about certain things. It's just statistics isn't one of them. So if I go second function entry, let's say I decide I don't need those parentheses. Darbo's full of himself. He has no idea what he's talking about. We can just get rid of those. It doesn't make any difference. All right, we'll try it. And you end up getting a goofy number, and you can't understand why because, well, you've done everything that I told you to do in the video. No, you didn't. You didn't do it correctly. Now, a lot of times people, let me bring that correct one up there, they'll say, okay, I'll go along with putting the parentheses in the numerator, but I don't see any reason why this needs to be in parentheses in the denominator. Well, again, if it's your goal to get the wrong answer, then don't put it in parentheses. You'll get the wrong answer there. What happens right here is your calculator will take 64.2 minus 63.6, and then it will divide by 2.5. It will calculate the answer, and then it will take that answer and divide it again by the square root of 50. Guys, you don't want that. You want this number calculated and this number calculated and divide this by this, not get into multiple divisions. So guys, what we would say here is we would say a sample mean of 64.2 from a sample of n equal 50 women is 1.70. Now guys, typically for z-scores it would be standard deviations. But guys, remember, we give this a fancy name here called standard errors. So guys, the interpretation would be this. Now remember, what I did is I ask you in this problem to find and interpret the z-score. So again, the z-score was 1.7. In the interpretation, we would say that a sample mean of 64.2 taken from 50 women is 1.7 standard errors above the mean. All right, guys, this one gets a little bit tricky. We get into price houses, which are positively skewed. So notice we don't start out with a normal distribution. And if I get back to my original drawing, if I can even find it, or not my drawing, but my original. Oh, shoot, guys, I got too much going on. Here we go. So number 3 here, right? We start out with the standard deviation. I'm sorry, we start out with a positively skewed distribution. So our population here is house prices. And the mean and the standard deviation are given because the mean is 315,000, standard deviation is 80,000. So just like before, except we don't have a normal distribution, we got something else. So guys, for us to be able to work these problems, for all this stuff down here in the central limit theorem to apply, we have to have a sample size of 30 or bigger. If we don't, we can't work the problem. So when we come down here, we say if a house, guys, a house is n equal 1, what is the probability its value is more than 400,000? Guys, we can't do this. Sample size has to be 30 or bigger. Same thing here, if n equal 12 houses. That looks more like the problem that we've been doing, but still, because we have a positively skewed distribution, n equal 12 still isn't big enough. We gotta have 30. Now, I don't know what's so holy about 30, but you can look at the simulations on these things. When n gets to be equal to 30 in non-normal distribution, something magical happens. It even works even better when we get to 100. But 30, good stuff happens. The central limit theorem starts to take effect. N equals 12, it does not. So, no can do. If n equal 40 houses, well guys, we got one we can work now, don't we? So what do we got? 315,000 and 80,000. Well, shoot, this isn't working at all. So, all right, that's about as good as we're going to get. So we have 40 houses. We want below 325,000. So second function. Well, all right, let's just go into normal CDF. So below 325 means I go from negative E99 to 325,000. Guys, don't use parentheses there because that would stop the number. So use 325. Make sure you get enough zeros there. Now we get into the parameters of the problem. We get into the mean and standard deviation. Mean is 315,000. Standard deviation is 80,000. But because we're doing 40 houses, we have to divide by the square root of 40. So our answer is 0.7854. So guys, the trick there, divide by the square root of the sample size. That's the one place where students get sloppy and A's turn into B's and B's turn into C's and C's turn into D's and so on and so forth, just because of this one simple thing. They don't divide by the square root of the sample size when they've got a sample mean problem. And there are these key words: average, average height, mean. All these key words in there, mean up here. All these key words that tell you you're dealing with a mean and average, so the central limit theorem kicks in. Back here, when you're dealing with one person, central limit theorem doesn't kick in. Okay, guys, that's all I got. I hope this was beneficial. You're going to have a couple of assignments, 7.2 and 7.3. The next video I'll probably put up tomorrow, or I'm not sure. It'll be a couple of days. I'm not actually feeling the greatest, to be perfectly honest with you. So I may not get it up until tomorrow or maybe even the day after. So